Hi class, let's take a look at problem 4. Now for problem 4, we have a piecewise defined function, and in this case, I'm showing here the pieces. For the first one is 3 for x is less than 1, so not including that portion, and then we are including a portion of the cosh function for x greater than or equal to 0. So this is going to be our cosh function. And the first part that we need to check is they're asking for all the intervals where the function is not continuous. So meaning where you don't have a continuity, we're looking from negative infinity to positive infinity. So in this case, the function is not continuous on, and I'm just going to put a bracket. So technically from negative 1 to the values of 0. And that's going to actually include this portion here where the function is in fact defined. So in this case, the function, once again, they're asking for not continuous at negative 1 to the values of 0. I'm including negative 1 because the function is not defined, and I'm not including 0 because the function is defined at 0. Okay, second portion. They want us to find the limit as x approaches negative 10. In this case, this is your negative 10, but coming from the right. So coming from the right, your value is going to be 3. In this case, this is just going to be the values of 3. They're not asking for us to show the properties of limits. All they want is the evaluation. So that's actually it. Once again, the notation says from the positives, in this case from the positives, you're going to have the y value, and in this case your y value, it's going to be 3. Let me move on to the next portion. On the next portion, they want us to use properties of limits to see if the limits are going to be defined. Okay, I added the actual graph. In this case, I'm putting all the arrows, and I actually zoomed in. Now, when we're defining technically limits, and in this case, this is going to be your x is equal to 1, the property of limits state, and let me actually pull up to the property of limits, that your limits are only going to exist if from both directions you're approaching the same y value. And that's the properties that they're looking for limits. In this situation, well, as you come from the actual positive side, as you approach 1, remember that this is in fact x is equal to 1, your function is going to approach 1.54 or the cosh of 1. So in this case, we said yes, the limit is defined since the actual limit as x approaches 1 from the positives of the function f of x is equal to the actual cosh of 1. And technically, that is the same as you approach from the left. So in this case, the actual limit as x approaches 1 from the negatives of f of x, this is also equal to the cosh of 1. So for us to conclude that the limit is defined, in this case, that has to be part of your statement. Your limit both from the right-hand side and from the left-hand side have to actually meet at a single point, which in this case, it's going to be the cosh of 1. Okay, that's actually it for properties of limits. So we need some sort of a statement that defines that the limit exists, and then also that from both directions your actual limits are defined. In this case, let me make this clear, that's the positive. Okay, last portion of this problem, they're talking about continuity. Now, for continuity, and let me display the property here. For continuity, we're talking about, well, your function has to be defined, and then also you have to check that the limits exist and that the actual limit and the function value happens to be the same. So for this one, we're only missing one portion, and let me display it again. So the function is continuous since both the limits of the function are defined, and you technically have that f of ln of 3, it's equal to the cosh of 3, and this is equal to the limit. So the only thing we have to add here is number 5, which says that the f of the ln of 3 it's equal to the actual limit as x approaches the ln of 3 of the values of f of ln of 3. So for your limits for the function to be continuous, we're checking one, that the function is defined. In this case, you can see that the function is defined. We don't have a discontinuity. Then you're checking that the limits actually are defined. So that would be 2 and 3, which implied 4. And then the fifth one is that not only the limits are defined, but they're equaling the same value. So in this case, the value of f of ln of 3 is equal to the limit. And that's it. So whenever they're asking us to check for continuity, you check the function value, you check the limits, and then you check the last one that they happen to be the same. And that's a way to show that, yes, the function is continuous at that point.